All right, let's test the mic here. You all good for the streaming back there? Okay, I'm getting a finger up here, thumb up. So anyway, well, hopefully that didn't go out. All right, so I'm Joan Horvath. My partner, Rich Cameron, is manning the booth out there at the Rocky Mountain Extreme Crowd by himself, so shout out to him before I get started. Yeah, all right. So thank you for all the folks who are here instead of Death Race Ring. Somewhat different crowd, I think. So what I'm going to talk about is our math modeling, but beyond just the modeling, I'm also going to talk a little bit about why we did this and where it all came from and all that good stuff. So we are based in Pasadena, in California, and we are, I'm going to talk a little bit about some work that was supported by a grant, so I always just acknowledge that. So we've been a company for 10 years now. Before that, we were a 3D printer company, so some of you may know my partner, Rich, as Huzawatsits. He developed the RepRap Wallace and the Bukito, and so you can see 2 years of evolution there, and I'm always amazed it's only 2 years. I always say in his misspent youth, I've aged him a lot. That was sort of the very first conference we did when we started this company. So we were a 3D printer company. A lot of you know about the race to the bottom in prices, and so that kind of did us in as a 3D printer company. We were two-thirds a D's maker. And so we said, well, what could we do that we couldn't be upended by all that race on price to the bottom? And we said, nobody's doing 3D printer training. So we started with 3D printer training. And eventually it turned out that a lot of our early customers in 2015 were schools. And a lot of them said, you know, we don't really know what to do with our 3D printers and our other makerspace stuff. So could you come up with some things and some curriculum? And so we gradually over time have gotten more and more into writing applications for the classroom for 3D printing. So we have 4 math books at this point, 3 geometry, trigonometry, calculus, and a teacher's guide to those 3. We also have a new edition of a science projects book. And we also have classes mostly about 3D printing, but 1 calculus class on LinkedIn Learning. And we do a lot of maker fairs because Make is our family now. So we do a lot of that stuff. So I'm going to talk a bit about our philosophy, why we've done things the way we've done it. If you haven't seen our booth yet, our booth is kind of in the far corner of this hall, and it has a thing that looks like a stained glass lollipop above it. I'll talk about what that is when we get there. So I'll talk about our philosophy, what we've done in 10 years here. What we see as some of the big challenges for using 3D printing in education, and some of the real possibilities and some of the power of it. So our philosophy is we believe in universal design, which is a term of art if you haven't ever heard of it. And the premise is that if you make something accessible for people with disabilities, a lot of our early work was for blind students. If you make things accessible for people who learn differently one way or another, very often it's good for everyone. And so even though a lot of our early work was for blind students, there's been a lot of interest from the hearing impaired community. There's also been a lot of interest from the autistic community to learn math somewhat differently. All of our models that you will see are made in OpenSCAD, and OpenSCAD is a free and open source constructive geometry program. I'll walk away so the whole screen's visible. It's a constructive geometry CAD for people who like to program. So you write a model in something that's sort of like C or Java, Python, a family kind of like that. And you get 3D geometrical primitives. I'll show an example. The program is free at openscad.org. There are block versions that people have to pay for. Don't buy those anyway because the subset that we use a superset. And a lot of those mostly are a subset, so you really can't use the block version with our stuff. And the nice thing about OpenSCAD, or the bad thing, depending on your point of view, is it's all text-based. That means that people who are blind, for instance, can use OpenSCAD with a screen reader. And so one of the interesting things we've interfaced with is the ability for people to use our models, even though they can't necessarily see a preview of them. And so we've had some interesting experiences with that, with people being able to alter our models even though they can't see the preview. So some of our results is we have 5 now repositories on GitHub. They're all linked on the bottom of our site, which is nonscriptum.com. I'll have it at the end. And they're all CC BY Creative Commons licensable, so basically you can use them for whatever you want. You just have to credit us and point people back to our book website, because it's nice if people buy the books, because that lets us afford to do more models. So hopefully you also buy the books. And if you're not familiar with GitHub, we have links on our page. Go to a site that basically says download models, or download contents of repository, and you click download. It's not very profound. So you'll get a big zip file of the models from that book. So you can do that. This is a screenshot from GitHub for our calculus. And we're up to over 100 models now, and all of our models are designed to be alterable. Well, most of them are. And so the idea is that you have a model, and then you or a student can play around with changing numbers on it, so that you have the ability to do a lot of different things with those, and not just download it and treat it like a toy. So a few examples of science projects first. So we have a botanical model, and the beauty of OpenSCAD is you can have parameters. So here we have some agave models and a couple of different flower models. Those are the same models as each other, with just a couple of numbers different in OpenSCAD. Because plants, a lot of plants, not all plants, people criticize this, the broad statement. A lot of plants like to lay out a Fibonacci number worth of petals or leaves and spread them out at what's called the golden angle. And so you get realistic looking plants as long as you keep those two parameters. Excuse me. And we also have a wing. We have one on the table on the display. And it's using accurate World War II airfoils. You can change the sweep of the angles, the taper, the length of the wings. You put it on a postal scale, as Rich is doing here. You blow a fan on it. Because you're blowing a fan on it, it generates lift. And so you can see how much lift this wing is generating, and it lets you put it at different angles of attack and play around with it. So it's a really good way to, we teach a class for 8 to 10-year-olds called Aeronautics and Astronautics, and they go absolutely berserk copying a lot of, trying to come up with different models. A little side note on this one, which was fun, is when I first looked up, I'm an aeronautical engineer by original training, I should have mentioned that. And so when we were first doing this, I said, well, the equations for these original airfoils, because they're actually a closed form equation you can write, the equation for these original airfoils, must be around somewhere. So I looked in Wikipedia, and the equations were completely wrong. So I said, okay, that's no good. So I looked at the references in Wikipedia. Those were wrong. I ended up finding a 1935 NASA tech report, or it was NACA at that point, tech report, with hand-drawn graphics signed off by Orville Wright and Charles Lindbergh, who were the NACA commissioners at the time. And so we cite that, and it's kind of fun to be able to find that kind of things. So anyway, it's interesting to try to make these models and to use sources that are very accessible. So we had these science books. They were modestly successful. People got excited about them. But people started saying, what I'd really like is to be able to teach a whole class as a maker. Can you do that? And somewhere along in there, we approached Make and said, we'd like to do that. And it was sort of a long and winding road with that. But what we want to do is take this universal design approach, hands-on, and do entire subjects more or less for the things that make sense to do hands-on. Sometimes people do hands-on no matter what, and it's sort of silly. So we try to do pull out just the things that actually make sense. So we now have geometry, calculus, and trig, and our calculus book is the most popular one by far, because people who are desperate to learn calculus are really desperate. And they also usually have their own money and not their allowance, so that makes a difference. So I'm going to talk a few about our sampling, what I like to call math experiments. People see math as a thing, right? But you can really do math experiments, right? You change the numbers, you change how your model looks a little bit. And so these are designed to let you do math experiments. And so we teach geometry first and then algebra. So that is, let us do some things which I'll talk about later. So this is a model that's on our table. It's attributed to Pythagoras. So, well, now you can't do it, because you know how it works. But we've been cornering people and saying, you want to do a math puzzle. So basically, it's a tetrahedron that fits inside a cube, and you have to know they have to line up one edge with the diagonal. And so once people have actually learned about this, they remember forever that the diagonal of a square is longer than the side. This is a model that was originally done for blind students. And it's a model that was designed to teach sine and cosine. So, excuse me. So here we have a right triangle. So we have a right angle here. We have a hypotenuse here. And we've designed it so that this hypotenuse is 1 in some units relative to the sides. And so the sine of this angle is just this opposite side over 1. So you can just read it off. And bizarrely, pilots always have been excited about this because they want to calculate crosswinds without looking. And this is not an FAA instrument, so no. I don't know if any of them went ahead and printed them anyway, but anyway, excuse me. You can tell the booth has been busy this morning already. So this is a fun one. This is attributed to Da Vinci. So you have a triangle, you cut off all the corners, you rearrange the corners, and the angles of a triangle add up to 180, and therefore you can also get half a circle. And so this is an accessibility thing. When Rich designed all the models. So when Rich first designed it, he has cut off the corners. And then you end up with 3 little triangles. You can't figure out what's going to go with what or anything else. So what he realized is that if he instead took off a little segment of a circle, then it was very obvious how to put them together. And so the blind students love this one. And it's a really good way to remember that the angles of a circle add up to 180. Because people sometimes say, is it like 215? But it's 180. So this model folds up. And so you probably, I have one here. So you've probably seen, if you're watching this online, I don't know whether you're also seeing me, but so you've probably seen paper things to make a cube. So they're flat kind of crosses of paper. And Rich's big insight was that if you instead filled in the volume so that you have pyramids, you can then fold this up. This is printed in TPU for cognoscenti. So if you then fold this up, you can reason about all the internals of this. So you can hand this to a blind kid, which we've done, and say, what's the volume of a pyramid? And they can reason it out because it's 1/6 of a cube. So it's really a very powerful model. It's a pretty short model in OpenSCAD. And it generalizes to all the platonic solids. So we have all the platonic solids. We originally did these in PLA, but for environments like this where kids are hitting their siblings with them, you kind of need the TPU strength for that. And there's a second version in the repository for TPU, which we have notes of. And this is the, let's see, that is the icosahedron, which is a lot of fun. So we also have a model that teaches about the unit circle. If you haven't learned about the unit circle yet, basically you have an X and Y and axis, and you, as you go around the circle, the sine or cosine or any of those functions varies. So this model takes graphs sine and cosine in the vertical dimension. We have an XY plane in the horizontal dimension. And the neat thing is that you graph sine and cosine, and then you roll it out onto Play-Doh or something like that, and you'll get your sine wave. So we're doing this on a little magic tablet outside because Play-Doh in this environment would be a bad idea. But it's a very powerful way to really understand that. You can do this with toilet paper tube too. This model's been around in some version for a long time. It's a much simpler model, but you can get some real precision here, and also you can have tick marks so you can actually see what's happening here. That model is, the model that you can see there is sine 2x. So it has 2 lobes on it. The model that's actually being rolled out, I think, is cosine. And you've probably all seen conic sections models. You can buy these for a lot of money. What this is about you have a cone and you make different slices along it. If you make a slice parallel to the base, you get a circle. You go a little bit steeper, you get an ellipse. You make a cut parallel to one side, you get a parabola. If you make a cut steeper than that, you get half of a hyperbola. You need another cone up here for the whole hyperbola. And one thing that people always think about is because there is one specific angle that you have to do to make a parabola, people always imagine there's only one parabola for a cone, but actually there's an infinite number. So we also have a model that shows that, and it's kind of fun that I've never seen a model like that. And we have it out there, and people want to put it together for different things, but it doesn't really work. Another interesting one is if you were an ancient Roman, let's see if I can avoid standing in front of this. If you were an ancient Roman, you had a rope to lay out things like arches. So I would have had a rope here, I would have swung it around and made my half circle arch. This is 3D printed parts with a little bit of museum putty between them. And so what you can do to demonstrate that, and we have this on the table, is you print this with the putty and then you lean on it and you discover it pooches out on the sides because not enough of the force is being transmitted straight down. But some genius in the Middle Ages a little bit later said, well, you know, what happens if I take my rope over here or my rope over here and I swing it out to make a half circle here, or fraction of a circle, and I come over here with my same length rope, I make this hemicircle, I get a keystone up here, and I get a Gothic arch, and you can lean on this just about as hard as any kid can manage to lean without collapsing the table first, and it's supported because the more of the force goes straight down. And so you can use this to talk about, you know, construction in the Middle Ages, about why different arches work. And then for fun, we also have a tracery, which is what the leaded glass, the lead that supports glass windows, a tracery model, which repeats this over and over. And it's fantastically strong, even though it's very fragile in this dimension, but very weak in this one. And so you can kind of see how you could have all that stone over a cathedral and actually have that work. So that model has been a lot of fun. We have a castle model that goes all the way through our geometry book that incorporates some of this stuff. And finally, a thing that we started as a joke, like many things. We had our calculus book, and so we said, you know, we had a little example of building a wall. And calculus is all about how things move and change. So we had a little discussion about a wall, and we said, you know, we could probably make this with Lego bricks, chuckle, chuckle. And then we looked at each other and said, ooh, hey, that'll work. So what this is, excuse me, is I have a wall, which is a little covered up here, which represents the curve x squared for people of you who have had calculus. So the wall is 0 bricks, 1, 4, 9, and 16 tall. And it turns out if you take some more bricks that are the difference of these, so the difference between these two is 7, so I have a 7 between them. The difference between these two is 5, so I have a 5 between them. The difference between these two is 3, so I have a 3 between them. The difference between 0 and 1 is 1. So my curve of differences, or my derivative, is a curve that's 2x. And so that's very visceral. And if I were to pile these back up, which is called integrating, I would get the original curve back. So that's called the fundamental theorem of calculus. So I like to say, with a handful of Lego bricks, that's first and second semester core concepts of calculus, and you can do some good stuff with that. But we also have a 3D print that is scaled to the Legos. So if you're teaching, it scaffolds directly. And so we have a 3D print that has x squared on one axis vertically, and then at right angles to it, we have the 2x. So you can talk about how you go one direction to integrate, the other to take a derivative, and you can go back and forth between them. And it's a lot of fun to see people say, well, gee, you know, is that it? It's like, yeah. And it's even more fun for circular functions. So a sine wave's derivative is cosine, which is at right angles here. You turn it again, you get negative sine, which is a derivative of that, and you can keep going. You keep going the other direction for those. And if that didn't make sense, you can come see the physical model. So we also have lesson plans, if you're so inclined, on our website, which is nonscriptum.com/projects. The lesson plans are CC BY, so they're freely available. So just scroll down on our projects page. You have to read through the ad about why you should buy our books first, and then you can download the models. So we have two major sets of models. One's geometry for teachers of the visually impaired, and so that was the grant-supported models. It covers some of the stuff that is in our geometry books and some that's in trig. It predates our geometry books, so the books are evolved and better because this was earlier. So they don't line up exactly because we have evolved a little bit, but they're a good starting place if you're thinking about how to teach from it. We also have one that's not related to the 3D prints, but it's called Designing Role-Play Projects with Microbit. And this is one of our students. We teach 1 day a week at a gifted place and kid place for gifted kids in Pasadena. And so what she has here on her shoulder is an electronic familiar. So it's a little dog that, as she moves around, wags its tail sometimes and lights up in front and all that sort of stuff. And this was a National Science Foundation developed program to see if you could interest girls in electronics more younger if it was involved in role play. So we've worked with some of these folks at UC Santa Cruz to develop some of these role play things, and they're all captured in a very step-by-step set of lesson plans for microbit. So those are freely available. Starts with a magic wand that you can wave around and go from there. So, you know, feel free to take a look at those, adapt them. Again, they're CC BY. We do have a lot of classes on LinkedIn Learning. Most of them are about 3D printing. They're kind of more corporate and industrial. We do have one that also covers the basics of our calculus book called Assembling Calculus. So LinkedIn Learning is what used to be lynda.com. If you're at some institution, your institution probably has a license for it. If not, there's free trials. And if none of that works, a lot of library systems have licenses and you can watch it in the library, and this is about an hour, if I recall. So it sort of walks through a lot of the calculus models, and it's a way to, if you're more of a video person, there's a way to do that. So let's talk a little bit about possibilities. So this is sort of what we've done so far. So one of the things we've discovered, this is a calculus student who his parents are very familiar with calculus. He's 9 in this picture. He's bigger now. This is a few years ago. But one of the things about this was his mom said, yeah, he's going to learn calculus. Sure he is. And he, came home pulled out his Legos and explained derivatives and integrals to his mom. And she was like, wow, okay. And so he got into it. And if nothing else, I say, even if they won't have the algebra yet, but they'll have a little bit of swagger for their 3rd grade math because they know a little calculus, and a lot of math is, as I'm guessing a lot of you are teachers in the room, a lot of math is confidence in saying, I can do this, and so even if they don't, take everything, there's a marvelous book called The Mathematician's Lament, and if you're in this room and you're interested in how do you teach hands-on, it's written by a high school teacher. And it's a marvelous little book that's, I think it's around various places online, but also at Harvard, one of the Harvard imprints has it out. But it says, in brief, his premise is that if we taught art the way we teach math, in kindergarten you'd learn to draw straight lines because you need it later. And in 2nd grade, you learn to paint, with one color because you'll need it later. And then by the time you got to high school, they'd say, okay, now you can actually draw something. And you'd hate art because it was boring, because you cut it into these little pieces that you'll need later, which is bad, right? So what we want to do is, I think calculus is where math starts really being fun, because it's applied, it's interesting, you can do powerful things with it. So our premise is if you can teach concepts of calculus in 3rd grade or so, then they'll be motivated for math after that, because they'll see where this is going. They'll say, oh yeah, I saw that concept and I see how this fits into a bigger picture, instead of, compartmentalizing so small that, it's like, ew, why am I doing all this drill? It gives them some motivation. So there's a little bit of everything. So we see that as a powerful thing. You can also do interdisciplinary learning. So this is one of our students making his familiar. So he had a whole story about this mouse. And one of the other kids in the class was making a snake, and it never occurred to them that snakes eat mice, and I never pointed it out, because that could have been bad, because the snake was a lot bigger, too. So this kid had a whole story about how brave his mouse was, and you knew it was brave because it had a cape. Now, why it has a picnic table cape, I don't know. He chose from many things, and across from the snake, too, and we were just waiting for this to happen, but it didn't. But he had a whole story. And, so that ability to generate that whole story and think about it is a powerful thing. We also teach a class called Medieval Battletech, where we teach them about technology of the Middle Ages, and then we rerun classic battles, and they make offensive and defensive secret weapons to improve their side's chances in that battle. So that is a castle done by a student who was probably 10 or 11 at the time in Tinkercad. So you can learn a lot about castles, what makes them defensible, all that kind of stuff. And all these are students at Institute for Educational Advancement, who's one of a marvelous partner for us in Pasadena. So you can learn, history is boring, some kids say, but not if you're figuring out how to fight off the, insert enemy here by having a secret weapon that's historically plausible. And Rich plays God, which is a role he really likes a lot, and decides whether it's historically plausible or not. So, and as I've said before, one of the things that we're very proud of is working with blind and visually impaired students. And our trig and calculus books, thanks to Make, working with us very closely, have EPUBs that have versions that are screen reader readable. So there aren't very many books out there just yet that have equations that a screen reader can read, parsed in a way that is plausible. So that is a technology frontier that's still a little rocky, but we worked pretty hard with Make to make that happen. So the trig and calculus books, which have a lot of equations, have MathML. The geometry book has, well, all of them have alt text on all the images. So if you know a blind and visually impaired person, this is a good game for them. So some of the big challenges, what we get all the time is, how do I teach and assess student learning? Rich likes to say somewhat cynically that math, as it stands now, has been designed to be easy to grade and not easy to learn. And there's some truth to that. But how can you teach and assess this with 3D printable models? And so we have some answers to that, which I'll get to in a minute. But one of the questions is, how do you also teach at a different speed? You probably all had kids in the class who say, I'm done. And very often, they're not actually done. So how do you give them some more interesting things? So because we got that question so much, this year we have a new book that just came out called the Make Math Teachers Supplement. And it's aimed at answering those questions. And so, for instance, what does show your work mean? I mean, show your work might mean write a lot of algebra, but show your work can also be, here's a model and I'm going to talk you through it. And so, if you're not I'm an algebra fan, and Rich is a geometry fan. And so one of the things we always do is that we'll talk about a concept, he'll develop a model in OpenSCAD. I'll spend 3 days of algebra proving that it's right to myself, and he always is. So that's sort of our in-joke that, he can do this in a lot less time. So in this book, the topics are arranged by the other books and chapter. We give learning objectives and sample projects, so how you can go through that. And we give some sample enrichment projects, because if you have a kid who's bored and who's going way out ahead of, what they quote unquote should be doing, you can let them run with this stuff and make some things, and maybe their fellows will see this and say that that's kind of cool too, and be interested and excited by that. So that's at least what we're interested in. So this is just a little example, of the kinds of things that we have, and you probably won't be able to read it. So this is conic sections and quadratic equations, which is Algebra 2 trig. So, one of the examples is develop an equation for a parabola based on focus and directrix. And so there are two, that's in both the geometry book and the trig book at different levels. And so it says, you can go do that, and you can do these examples to try to meet those objectives. So we have a lot of lists like that. So if you're a teacher, you can flip around through it. We also have examples that if I have a particular objective, like this one is compute the volume of a cone, sphere, or cylinder given the radius and height, and then show the ratio between the three volumes experimentally for a set of shapes that all have the same height and radius. So more slowly, what that actually works out to be is we have a hollow cylinder, a hollow cone, and a hollow half sphere. And the idea is you can pour salt or something into it. I always like to say you can make money in bars because no adult remembers any of these relationships. But it turns out a cone is 1/3 of a cylinder, and a cone and a half sphere that meet these criteria together work out to a half cylinder, to a cylinder that height. So the assessment is go make the models, this particular model, and then measure sand or water to fill the volume. So that's a way to assess it, show it empirically. And it'll stay with you instead of, what's that formula again, I had a guy come up to the booth recently and said, there's no pages of formulas in this calculus textbook. I said, yes. And he said, well, how can it be useful? And I said, well, that's kind of the point, because it's different than other books. All right, so to kind of wrap this up a little bit and leave a little time for questions. So we have 13 books now, I think, something like that, if you count editions. Our website is nonscriptum.com, and I've talked mostly about the projects and classes tabs here. On our classes tabs, I'll point out that we have a teacher or homeschool parent course in Pasadena, July 23rd to 25th, I think. I'm not sure. I can never remember the date. We just changed it because it turned out we were going a little bit too late. July 23rd, 25th. And so that's a 3-day class in teaching with MakerTech. That will be at various levels. So if any of you are interested in a little time in beautiful Pasadena in July, or a teacher, that would be great. Make has created a little dedicated area for just our math books, so that QR code there will take you, or bit.ly Make Math will take you to our the page for our math books. All our books are on Amazon. The math book is on, the science books are on Amazon. And so you can email us. I'm Joan at Nonscriptum, Rich is Rich at Nonscriptum, creatively enough. We're the entire company. Please don't email me trying to sell me services for remote programmers and all the other things. I get about 10 of those a day, which is annoying, but it's all good. But if you're interested in what we're doing, or if you're a teacher and want to pilot some things and talk to us, we love feedback. And we're very grateful to this community and to the organizers here who have been very good to us all along. So I'll stop there and then take some questions. So thank you. Okay, so a question, yes.
Do you have any books on OpenSCAD?
Do we have any books on OpenSCAD? Not really. The geometry book talks you through OpenSCAD in the context of its geometry, because it's constructive geometry. So we use OpenSCAD as a demonstration for that. Sometime in this summer, we'll link it onto our site. We just finished a project for an association of blind schools for the blind, starting up OpenSCAD for people who are blind to teach them to make 2D objects that they can then put out on they have these little embosser things. And so we have an OpenSCAD, very step-by-step, that will come out on their site then. But basically geometry ones. But the reality is the OpenSCAD documentation is so good that, it's sort of superfluous. Other questions?
What's your biggest challenge in teaching or hurdle you come up against when you're showing these concepts to children?
So the biggest question is, what's the biggest hurdle you hit trying to show these concepts to children? School boards. We gave a presentation at a school board that will remain nameless, and they said, God, this is great, but if kids go home saying they had fun in math class, parents are going to call us and complain. I cried all the way home. This was a long time ago, because it's so against the purpose. Because they just see it shouldn't be fun, it should be suffering and pain, and otherwise you're not learning, and so that is the short answer. The fact that textbook adoption is a very, very long process. So we are not textbooks. We are not covering the approved step-by-step thing that is in any given state, because that would kind of water down what we're doing. What we're trying to say is, here are things that really lend themselves to learning hands-on, and so it's a supplemental book. So the idea is, if you're teaching, in any particular subject, that you can take a look at this book and add things to it. And so that's how most people have been using it. Our other big market is homeschool parents. So a lot of homeschool parents have been high energy. And homeschool parents are very definitely welcome at that event in Pasadena. Any other questions? Other than my plants here? All right, well, thank you very much for being a good audience and missing the Death Rachers to hear it, and hello and out there in streaming land.